In this problem, we are given a Venturi tube. So Venturi tube is just a tube with varying cross-sectional area such that the cross-sectional area first decreases, and because of this, the local velocity increases momentarily. And from Bernoulli's equation, we can tell that the pressure then will decrease here, and then there is a diffuser section where the fluid coming through this constriction, it expands and its velocity drops again, and so that the pressure increases again due to the Bernoulli equation. So let's say Q is the flow rate of air through this Venturi tube. Then uh, since because of the conservation of mass, Q is the same throughout the Venturi tube. So if I mark these points as A, B, and C, then the velocity at A is q by A1, and velocity at B is q by A2. And since A2 is smaller than A1, that means the velocity of air at B is larger than the velocity of air at A. So Bernoulli's equation tells us that PA plus half rho VA square is equal to PB plus half rho VB square. And since the velocity at B is larger, it means the pressure at B is smaller than pressure at A. So if pressure at B is smaller than pressure at A, then you can imagine if this pressure drops to a very low value, and the pressure here is P atmosphere, and if the pressure at B drops below P atmosphere, then basically water will climb up in this tube. And in this question, we are asked to find the value of flow rate Q, for which the water climbs all the way up to the Venturi tube. And as you will see in your lectures on flow measurements, Venturi tubes are usually used to measure the flow rate of air or whichever fluid is flowing through. So the basic principle in that case is that basically uh, we in, we introduce artificial pressure drops across these cross sections, and we measure those pressure drops, and we can then relate those pressure drops to the velocities by application of Bernoulli equation. And if we know the velocities, then we can calculate the velocities from the pressure drop, and if we know the velocity, we can get the flow rate. So that will come later, but right now let's just solve this problem. So I already marked the point at the entrance as point A, the point where the throat is point B, and the exit is point C. Um, so let's just write out the pressures. So PA is, let's say we don't know what PA is, it is not given here. PB again is an unknown. However, PC is known because point C is open to atmosphere, so PC is P atmosphere. And we can write the velocities at A, B, and C in terms of the flow rate. So velocity at A is flow rate divided by the area at point A. Similarly, velocity at B is flow rate divided by area at point B. VC is flow rate divided by area at point C. So area at point C and area at point 1 are the same. So what this basically tells us is that VA is equal to VC. Now, let's see if the assumptions for Bernoulli equation are true. The first one is inviscid. Uh, Again, so so at each of these cross sections, we will assume the flow velocity to be uniform like this. So we will assume that there are no velocity gradients across the pipe cross section. So because there are no velocity gradients, the flow will effectively be inviscid. Second is incompressible. So the flow of air is incompressible if its Mach number is less than zero point 0.3. We will just assume that air is not flowing that fast. So it behaves as an incompressible fluid. Third is steady. So this is true because the flow rate Q is a constant. It is not changing with time. So that means we can apply Bernoulli equation along a streamline. I'll just draw the streamline. So let's just say this is the streamline along which I'm applying Bernoulli equation. So first is, since we know the pressure at point C, let's just apply Bernoulli equation between point B and point C. So PB plus half rho VB square is equal to PC plus half rho VC square. Notice that there is no rho GZ term here because the Venturi tube is at a fixed height. So this streamline is completely horizontal and Z is not changing. So I just omitted Z while writing this equation. So PB PB is an unknown, but PC is P atmosphere. VB and VC are known in terms of flow rate. So substituting everything here, we can find the value of pressure at B. It comes out to be P atmosphere plus rho Q square divided by 2, 1 by A1 square minus 1 by A2 square. So this is the pressure at B. And as I mentioned, if pressure at B is smaller than P atmosphere, then the water will climb up. So if you look carefully at this equation, the pressure at B will be smaller than P atmosphere if this term is negative, and basically A1 is greater than A2. So 1 by A1 is smaller than 1 by A2. So that just means 1 by A1 square minus 1 by A2 square is negative. So that means this term, the second term on the right hand side is negative. So pressure at B is indeed smaller than P atmosphere. So we now want to find out what the flow rate should be such that the water climbs up all the way to this height h. So to do that, we will use simple principles of hydrostatic pressure that you use to find out pressures at different heights in a manometer. So I will basically start from this point and go up till uh, till point B. So simple hydrostatic pressure tells me that P atmosphere, which is the pressure here, minus, since I'm going up and I need to subtract rho H2O because this is water. I'll use the water density GH is basically pressure at B. So this is one equation for pressure at B. This is the other equation for pressure at B. And if we equate them, we will basically find out the unknown Q. So PATM plus rho Q squared by 2. Remember, this rho is air density because we are applying the Bernoulli equation between points B and C, and air is flowing uh, from point B to point C. So this density is the air density. Then in bracket 1 by A1 square minus 1 by A2 square will be equal to PATM minus rho H2O and GH. So PATM minus rho H2O G capital H. So PATM will cancel out, and this gives us Q to be equal to square root 2G capital H, the ratio of density of water to density of air, and this term which includes area. So this is the flow rate for which the water will climb up all the way into the pipe. Uh, and also again, we can also determine the pressure at A now by simply applying Bernoulli's equation from between points A and point C. And since velocity at point A and C are equal, the pressure at point A and C will also be equal, which is equal to P8 atmosphere. So, so since so this is a very interesting result because the air is flowing even though there is no pressure difference between point A and C. Um, you might be familiar with the fact that for making a fluid flow through a pipe, we need to apply a favorable pressure gradient. But here, since pressure at A and C are equal, how is that? How is the air flowing? So that's because we are neglecting any viscous losses while applying Bernoulli equation. But in real life, there are viscous losses due to the friction between the air and the pipe walls. So because of that, you will need a higher pressure at A than pressure at C to make the airflow. But since we are assuming it to be inviscid, the pressure at A and C are equal. So that's it for this problem.